Just more color physics here. Just want to look a little bit closer at moments of inertia. What I really wanted to look at is a continuous mass distribution. Now, while everything is made of discrete point masses, protons, neutrons, and electrons, generally speaking, doing some from I equals 1 to 20 trillion doesn't really sound too beneficial for anybody. If we can approximate an object that is extended as being more of a continuous mass distribution, then hey, we can start integrating some, doing some crazy sums. And that's generally what we want to be able to do. Just invoke the idea of integration to add up all the individual contributions of the individual mass elements relative to some axis of rotation. So if we're talking about moments of inertia for continuous mass distributions, we can write that moment of inertia, I, is equal to the integral over the mass elements of m r squared dm. So the individual mass elements themselves are at locations relative to the axis of rotation, some radial distance away from it, r, and this is what we ultimately write out for the consequential continuous mass distribution. So we can think of some extended object. Take something simple here. Consider some just line mass. One-dimensional mass is a continuous mass distribution, but we want to be able to figure out what is its moment of inertia relative to some point. That point's somewhat arbitrary. It doesn't necessarily need to be on the object. It just depends on where you want to define it relative to. Where is it going to be spinning relative to? So let's just say we're here. We're going to put an axis of our rotation right there and ask, what is the moment of inertia of this object? What we got to be doing is thinking about the contribution of all the individual mass elements. So you take yourself this, right? There is some dm there, and that dm is some distance r away. And, well, when we're adding up the individual contributions, it's mr squared, so it's dmr squared. Integrate over all of the mass elements. So when we got this line mass here, we have all these individual mass elements are different radial distances away from the axis of rotation. So we got variance in r with respect to the individual mass elements. So how are we going to approach this? Well, we need to have some sort of notion of how the mass elements are laid out in space. Just saying dm makes it a little bit hard to integrate over. Saying, well, we're integrating over all the mass elements. So what we can do is define what is known as a linear mass density. Linear mass density, this is a lambda. Linear mass density is really mass per unit length. In terms of the idea of it, that's what it's a measurement of, the mass per unit length. Now, linear mass density can be something that's constant, which means that you could cut this up into a bunch of equal lengths and you'll have the same amounts of mass because you've got a constant linear mass density, a constant distribution of mass, that is. Or you can have that maybe as you go this way, it gets denser and denser. So that if you cut it into equal lengths, you have that they don't all have the same amount of mass because you've got a variation in the linear mass density. So if the linear mass density is constant, we can just say that it is the mass divided by the length because it doesn't matter. But if it's not constant, then you have to start thinking about, well, representing it in a different way. So if lambda is constant, lambda is equal to m divided by L. M's the mass, L's the length. That's great, mass per unit length. If it's not constant, if it varies across the object, we can still look at it in terms of the infinitesimal mass elements. We can write this, that dm is equal to lambda dl, where lambda is a function that describes the variance of it. Really, this is the definition, or how we can relate the infinitesimal mass elements to the infinitesimal length elements, and a characterization of the linear mass density. Really, whether it's constant or not. If it's constant, that's great. It's just an m divided by L. But if it's not constant, we can have some function that describes it. This is important here. It's important. How do we get that? Multiply both sides by L and look at what is dm dl. And that's what you get out of it, right? So, at that, we can take this dm now and rewrite it in terms of length elements, which is a little bit nicer to do. And of course, the linear mass density. So this can be written as r squared lambda dl. And what are we integrating over? We're integrating over the length with respect to the distance away. Integrating over the length of the line. So, what we want to be able to do is actually quantify something out with a linear component. We can look at, well, what if it's not just a line? What if it's extended in 2 dimensions? It has some area, or has some volume. Then what? Well, this is the simplest sort of mass distribution that we have. It's a line mass, but for continuous distributions. Well, let us just take a look at this. So let us now take a nice little coordinate system here. And we're only going to worry about 1 dimension. Let's say that this object doesn't have any thickness, it's just a line, and we're going to say that it exists from x equals 0 to x equals L. X equals 0, x equals L. And we're going to ask, what is the moment of inertia? This line mass. Now let's say that the total mass is, it doesn't really, we don't need to quantify it. We'll just say total mass m. Total length is L. And that's what we've got going on. So what do we want to do? Well, before we can start worrying about computing or developing what the expression for the moment of inertia of this object is, we have to define an axis of rotation, or define a point at which we are measuring things relative to, measuring the mass distribution. So let us take this end right here and say this is where we're going to be measuring the moment of inertia relative to. We'll say this is the axis of rotation. At x equals 0. So we've got all these mass elements that are contained within length elements now. Those length elements are really a bunch of dx's because it all lies along the x-axis. So we've got this little dx right there, and in terms of dm, the infinitesimal mass element that's contained within here, dm is equal to lambda dx. All right. So we have some length, and then we have some mass within that length that depends on what lambda is. So we're going to go ahead and let lambda be equal to a constant, and kind of go from here. So we can go ahead and take our expression there and say for this, that the moment of inertia goes from where we start to where we end. So we're going to go from 0 to L across the entire length of this object. And our r squared is our distance from this point here to the mass elements in question, which is just x squared because it's all on the x-axis. So we call it x squared. And then our dm is lambda dx. So what do we get out of this? Well, let's just go ahead and integrate this, right? So lambda is a constant, so we just got the integral of x squared. That's x cubed over 3, so we got lambda x cubed over 3 evaluated from 0 to L. So we've got lambda x cubed divided by 3 evaluated from 0 to L is equal to lambda L cubed divided by 3. All right, so there's the moment of inertia relative to the end of the object. Depends on the length of the object, yeah. And it depends on what lambda is too. Let's go back. Lambda is equal to a constant, right? If lambda is equal to a constant, it is the total mass divided by the total length of the object. So for this, we have that it is m divided by L times L cubed over 3, which is equal then to 1/3 m L squared. That is the moment of inertia of a one-dimensional rod, we usually just say a rod, with a mass m, a length L, a uniform mass density, constant mass density. That's it, 1/3 ml squared. This is the moment of inertia of it. So now if we want to spin some object, say it's like a meter stick, we want to spin it around from its end, and we have some specific angular velocity that we're spinning it at, we can go ahead and compute what its rotational kinetic energy is. 1/2 I omega squared, where I is 1/3 ml squared. I want to do something else. What happens if we pick a different location to be the axis of rotation? Is that really going to change what the moment of inertia of the object is? The answer is, yes it is. So, let us consider this. Let's erase all of this. So we consider the same line mass, if you will. Say the total mass is m. L's the length. Say that lambda is equal to a constant. Take this. We've got ourselves this little coordinate system. And again, let's just throw it on the x-axis just for the sake of ease. But now I'm going to say we're going to go from here to there. Oof. It's a little bit different, but like this. We're going to say that the center now is the axis of rotation. This is still going to have a total length L, but now we've got that this is x is equal to L over 2, and this is x is equal to negative L over 2. So we go negative L over 2, x to there. But again, we want to know what the moment of inertia is relative to this location now, the center of the object. So, what do we need to do with that? Well, we just do it. We figure out the same sort of way. This side has mass elements that are different distances away. This side has mass elements that are different distances away. And again, it's the distance. It is not the coordinate. So you've got to be a little bit careful with that. But nonetheless, we have this. We've got this side here. Let's just look at this side. For the right side, we've got that the moment of inertia is going to be equal to the integral from 0 to L over 2 multiplied by x squared lambda dx. So we've got the same sort of thing when we're just integrating over this side relative to this point, except instead of going from 0 to L, we're going from 0 to L over 2. All right, what does that come out to be? It comes out to be something that basically you've already seen. Right? So let's do this. RS for right side. So we know that this is going to be equal to lambda x cubed over 3 evaluated from 0 to L over 2. That's good. What's that going to be? Well, we've got an L cubed over 8 times 3 is 24. So you've got lambda L cubed over 24. All right. Well, what else do we want? That's just for the right side. What for the left side? The left side is going to kind of give us the same contribution because really, again, it's a matter of how far away the elements are from the axis of a rotation. That distance can't be negative. Even though we're going over on this side from 0 to negative L over 2, the distance goes from a distance of 0 to a distance of L over 2. So for the left side, we still have that I sub the left side is going to be equal to the integral from 0 to L over 2 of x squared lambda dx, which is the same thing that we just had here, which is lambda L cubed over 24. So because we broke this up into even segments, we get equal moments of inertia relative to the center on either side. But really, we want the total moment of inertia. The total moment of inertia is going to be both of these joined together. I is I right side plus I left side, which is equivalent to 2 times I of the right side or 2 times I of the left side, but ultimately that becomes being equal to lambda L cubed over 12. 1/24 plus 1/24, 2/24 is 1/12. Then we can go ahead and evaluate what lambda is. Again, lambda is m over L. So we've got that I, the moment of inertia relative to the center of this, is going to be equal to 1/12 m L squared. Relative to the end, 1/3 ml squared. Much different. Much, much different. So it's a different mass distribution, that's why. So this is ultimately some moments of inertia that come in handy. And really what you can always do is you can always break a compound object up into different pieces. The total moment of inertia is going to be the sum of individual moments of inertia that you compute relative to the same location. So sometimes it's a nice tool because maybe we want to put like a circle on the end of this, not a circle, but a sphere or a cylinder or something on the end. And then we want to know what's the moment of inertia relative to the center of that sphere or something like that. And we can start adding things together. There's one other thing that goes with this, and usually, there's not one thing, there's a bunch of things. Usually, start doing it in like count 3, where you've got yourselves double integrals, triple integrals, but for extended objects, with an area of mass, we can define area mass density that's my sigma. A lot of people like a little bit curvy. I like doing it like that. but we can define area mass density, sigma, and we can note that the mass elements themselves will then be sigma dA, where dA is the area element. Or volume we can define volume mass density rho, there's my rho, which is the mass per unit volume, and I can write that as the mass elements is rho times dV. So we're not going to really do any of these. So we can do something with this one just to see something really quick. But for the most part, calculus 3, you'll see a bunch of nice problems because they turn into really fantastic integrals to solve out for crazy mass distributions. Consider this. Consider a solid cylinder. With a uniform area density, sigma is a constant. Moment of inertia. Relative to its center. Plane aligned along with the cylinder. So we've got to make sure that we're going to consider spinning it like this and not like this, because that changes the mass distribution. We've got a different axis. We want a nice central axis like this. Well, we've got this to consider, right? We want to go ahead and figure out the total mass distribution relative to the center and say that this cylinder has some radius r. What are we going to have? Well, we've got ourselves that the moment of inertia is equal to the integral over the area of r squared dA. So again, we're going to take the point at which we're integrating this r over being the center of this circle here, so that we're defining the moment of inertia relative to the center. So how can we get dA? Well, a couple of different ways that we could go about this. Easy way, hard way. We could write dA is equal to dx dy. And then note that we got to break this up into a double integral. That's okay. Or dx dy is r dr d theta. You've seen that or not before? I don't really know, but this is transition between polar to, Cartesian to polar. Anyways, at that, we can write then that I is equal to the integral over r from 0 to r, and the integral of theta from 0 to 2 pi of r squared r dr d theta, which is then that double integral 0 to 2 pi 0 to r of r cubed dr d theta, which, well, we can do the r first, right? So we'll get r, so I hope I need to throw sigma in here, sorry, I'm getting ahead of myself. Sigma, 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 sigma dA for the dm, sorry. And, well, the sigma is just a constant. So we can write this as sigma. And we've got r to the 4th over 4. So r to the 4th over 4, evaluated from 0 to r, d theta from 0 to 2 pi. So there's no theta dependence for r. This is just going to be r to the 4th over 4, which we could really just pull out. We know that the integral of d theta is just equal to theta from 0 to 2 pi is just going to give us a factor of 2 pi. So what do we get with this? We've got ourselves sigma multiplied by 2 pi multiplied by r to the 4th all over 4. So there is the moment of inertia relative to the center for this solid cylinder. Whew. So what can we do with this? Again, we know what is sigma here. Sigma is equal to a constant, so it is the mass divided by the area. What is the area of a circle, cylinder? Just going to be equal to pi r squared. So in the end, we've got ourselves that I is equal to m divided by pi times r squared multiplied by 2 pi r to the 4th divided by 4. Let's see what happens here. The factor of r squared goes away, factor of pi goes away, and a factor of 2 goes away, leaving us with 1/2. So we got ourselves 1/2 m r squared. I said that before, but we can kind of show it pretty easily. That's it. There's a moment of inertia of a solid cylinder about its center, assuming the rotation is in the plane of the circular cylinder itself. All right, so now it's one last thing. And that last thing is about compound objects, which can make your life really, really easy, especially for some tough calculus type of problems. There is what is known as the parallel axis theorem. The moment of inertia is unknown relative to a location other than objects center of mass then I is going to be equal to I times the center of mass, ICM, which is moment of inertia relative to the center of mass of the object, plus md squared. ICM is the moment of inertia relative to the center of mass, which for things of continuous mass distributions, and go ahead and take in like a cylinder, is at its geometric center, or for a sphere with a continuous mass distribution at its geometric center is where the center of mass is, the place where you can say that all of the mass is contained in a point, even though there's a distribution of it. We'll define that more some later. But ultimately, if you know what the moment of inertia relative to the center of mass is, which this would be, and you want to know what the moment of inertia is relative to some other location, we just add on this factor. So this factor here is d is the distance from the center of mass to the new location. So this is ultimately known as the parallel axis theorem. And it can be used to figure out what the moment of inertia is for a more complex mass distribution. So for instance, what happens if I take a mass like this and say, I'm not going to rotate it about its center, I'm going to rotate it about its outer edge like this. Well, what's the moment of inertia relative to the edge of the object? It's much different mass distribution than, well, that relative to its center. We can agree with that. So if we took the cylinder, there's its center, and then said, you know what? I'm going to make its axis of rotation here. That is a distance d away. Well, what's going to be the moment of inertia of this object? I is going to be ICM. This is center of mass is at the geometric center, plus this md squared. M is the mass of the object, total mass, and d is the distance away from the center of mass to that new axis of rotation. So for this, we would have, and that's 1/2 m r squared plus m d squared, but d is equal to r if we're on the outer edge. So we've got that this becomes 1/2 m r squared plus m r squared. So got 3/2 m r squared. If instead you wanted to figure out how to integrate all the different mass elements relative to this spot here, much more difficult. Not that it can't be done, they make some crazy cool problems, but the parallel axis theorem allows one to determine the moment of inertia at some other point that is in the same plane as the center of mass's moment of inertia that was calculated. Will come in handy at some point. Maybe not this semester, but maybe the third semester, like pendula and stuff. Anyways, that's it for now, and be well.